Alright, it's time again to start. One more thing about the characters polynomial that I didn't say yet. If you take the characters polynomial and you plug in the matrix C, you get it 0. So that means you evaluate So, for example, what we had here in the table, the x squared plus x plus 1, if your p of x is x squared plus x plus 1, then you're seeing here that you're supposed to take c squared plus c plus the identity matrix. And that one will give you the all zero matrix. Now we also know something about the order. So if you have that the order of C is some integer d, that means that C to the d is equal to I. So for instance here, in that case, we had that c cubed is equal to I, or if you move the I on the other side, so c cubed plus identity matrix is 0. So there's a difference in that for the order, we only want one term plus I is 0. And for the characters polynomial, you have multiple terms, and the degree is limited by the order of the LFS R. But there's, of course, a very close relation between those two. Now, we actually want to leave matrices because matrices apparently introduce interesting errors in different algebra systems. And so we now introduce the order of a polynomial. So let p of x be the characteristic polynomial of an LFS R. The order of f, or period of f, well, order of f is the smallest non-zero integer d with, when you compute x to the d and you reduce it mod f of p, this polynomial, then you're getting 1. Let me put it here. So let's do an example. So we have our p of x as the x squared plus x plus 1. Alright, so we're taking x to the 1 is equal to 1 mod p. Nothing interesting happened here. Now x squared, and we're reducing modulo this thing. So similar to reducing what 7, where we're looking for multiples of 7, here we're looking for multiples of this. Well, it fits in once, and then we have some remainder. So x squared, if we divide by this thing, then we have a remainder of x plus 1. So x squared is common to x plus 1 mod p. Now something happened, but this is still not equal to 1. All right, next try. So we're taking x cubed which we know is the previous one, that's x times x plus 1, which is x squared plus x. And again, we're replacing x squared by x plus 1. So that's x plus 1 from the first term, plus x from what's already there. And now this one is actually 1 mod p. So the order of p of x equals x squared plus x plus 1 is 3. If you prefer, yeah?
So shouldn't x be something different than 1 mod p?
Totally. This should be x. Alex, thank you for watching. There's no reduction on this. One thing is, we always want to have an expression over here which has degree less than the degree of p. So we always reduce the right-hand side mod p of x and get a poly of degree less than k. Now I didn't erase this one because I want to add another column to it. So if I want to have here the order of p of x, then we just computed this one has order 3. If you now sit down and do this for all of them, then we're getting 7, 4, 105, and 126. So it looks very much like the order of p of x equals the order of c. This is something which you could just type in if you have those polynomials still there from when you did the factorization. You do a loop and you compute all the powers of it. Then you would see that the first time that you negative 1 is exactly after the same as when you're getting to the 126. And that's not a surprise. I mean, the way that I defined it would probably have looked more natural if I had said, well, this is the order of x mod p of x. So let me give this as a note. And I think, yeah, get all the comments in that part. So note the order of p of x is the same as the order of x mod p of x. So if I give you the polynomials modulo p of x, so then you have a set, and I can define a multiplication on there. At least it gives you a semi-group. You might not be able to divide, depends on the polynomial, if it's irreducible or not. But you can define multiplications. It will stay in the set. if you have a polynomial of degree less than p of x, you multiply, you reduce, you get another polynomial. Now, if you would hit at any point a factor of p of x, then you would get 0. So the claim is that this one will actually be non-zero, so you'll run through all possibilities until you hit 1, and then you start again with x. So if you take the whatever field you're in, let's take f2 because it's our example, f2 of x, mod p of x is not necessarily a field, but powers of x will not be 0. So powers of x mod p of x will not hit 0. So reach 1 at some point. Now the nice thing about this is, if you believe the equivalence of the order of p and the order of c, is that instead of figuring out what is the smallest power of c so that we get 1, we can just take the smallest power of x modulus polynomial. So instead of dealing with a clunky k by k thing, we're just dealing with polynomials of degree k. Well, degree less than k strictly. So at most k coefficients, so linear in k instead of quadratic in k. And then the orders are equal. Because p of c is 0, so c plays the role of x. When you reduce mod p of x. So this is the same that I was saying, okay, when you're solving exercise 3, you have your alpha. The only thing you know about alpha is that alpha squared plus alpha plus 1 is 0. Here we have, well, whether we take the matrix, there we know it's the root. But we can also just take a symbol that's called x. And then the only thing we know about x or c is that it satisfies this kind of polynomial. Now I have two things to go through. One is something more about how we can compute this. I think I'll start with that one. And then something about actually showing not only that these are equal, which is kind of, well, just by definition these are the same, but also why these are equal to the maximum period. Okay, so let me start with the thing about irreducible polynomials. What is your computer doing inside? Is it really doing like trial division by all the polynomials? It's not. There are polynomial time factorization algorithms which we're not covering in this class. What we are going to cover briefly is how can you determine whether a polynomial is reducible. That's like finding a number and saying is it prime or not. And actually for polynomials, these irreducible tests are pretty easy to write down. There's a nice one due to Rabin. So Rabin's irreducibility test. So somebody gives you a polynomial and you want to find out is it irreducible. So a polynomial. Now we do it in general again, so I call it f of x again. It lives in some finite field fq. So this could be the field of two elements that we've been working with so far. It could also be a general field. Put f7 there, put f4 that we just defined there. We will only use it for q equals 2. On the other hand, since I'm stating it, I might as well state it in full generality. Of degree f is n is irreducible if and only if. Okay, so we now have to look at two conditions. One is that if we take our polynomial f of x and we compare it to a polynomial of much higher degree, that's x to the q, that's the same q as up there, to the n. So this is the degree that comes in, and this is a field size. So for us, this is 2 to some power. So x to the 2 to some power. Say in this example, we're having a degree 2 polynomial over f2. So we're having x to the 2 to the 2, so x to the 4. Down here we have a degree 10 polynomial, so this will be x to the 2 to the 10, so x to the 1024. This is a pretty damn large degree polynomial. So we need to figure out how we can do this test actually computationally, but the good thing is we can. So this thing minus x is divisible by f. So what you would do is you take this gigantic polynomial and you check whether f divides it. And part B, for every divisor d larger than 0, which is a divisor, well, n strictly less than n, which is a divisor of n, so of the degree. We have the GCD, greatest common divisor of this polynomial f of x. And now instead of having n there, we put a d. So the polynomial x to the q to the d minus x. For n, it should be a divisor, so that means we're getting f of x. And for anything smaller, this is just 1. So they're copron. There's nothing in f which divides that. Now the reason is, if f has smaller factors, if f would have, say, take our degree 7 polynomial again, if our f has a degree 3 and a degree 4 factor, then the degree 3 factor would take this polynomial with degree 3 here and divide it, so this GCD wouldn't be 1. And the degree 4 factor would be a common GCD of this with d equals 4. So if you believe that every irreducible polynomial of degree n divides this thing, then it's very clear that a polynomial that factors will hit one of those conditions. Now this part up here, if you want to prove these things, then you really get into how fields are constructed. Then you'll see that this thing actually constructs the field of fq to the n elements, and so divides it. But if we just take as an axiom that for an irreducible polynomial of degree n, this division holds, then we see down here why we have to catch everything that has factors. So I just made the example of the degree 7 polynomial, because I remember those factors. Over here, this degree 10 polynomial, if we would put this in, we see that this thing has a factor of degree 2, so there's an x squared plus x plus 1. Now, this degree 2 factor would divide x to the 2 to the 2, so x to the 4 plus 1, plus x. And so we would catch this polynomial in this GCD. Now, you can save some effort if you watch out. You could do like only prime divisors and then n divide by d and so on. So we can save some work here. If you want to implement this thing, you don't need to test all. It's sufficient to compute q to the d, well, n divided by pi minus x for pi, the prime divisors, this thing suffices. But we don't care about this. We actually care about the A part. Very quickly, as an example, let's try the first one. We know already. No, actually, let's try the second one. We know already this one doesn't have factors. Let's try that one. Or, hey, we haven't tried this one yet. X cubed plus x plus 1. So example, there was a claim that x cubed plus x plus 1 over f2 is irreducible. Now, how do we compute this thing? We would start at b. So I want to build up to needing x to the 2 to the 3 minus x. So I start at b. Okay, and now for b, I have to do this for all divisors of n, and there's 3 here, so that's not too bad, which are not equal to n. So the only divisor I have to look at is 1. So I have n is 3, d is 1. So I'm looking at the GCD of x cubed plus x plus 1 with x 2 to the 1, well, minus plus the same, so plus x. Now 2 to the 1 plus 1 is not too bad. I can reduce this, but x to the 3 plus x plus 1. Nothing happened. There's remainder is x squared plus 1. Then I do a trial division of, divide x cubed plus x plus 1 by x squared plus x. And I'm getting x cubed plus x plus 1 divided by x squared plus x. I'm getting, fits in there x times. I know that here you write things yet again differently. I'll just do one style that I'm most familiar with. So I'm multiplying now x in there, some x cubed plus x squared. Left over is x squared plus x plus 1. Fits in 1 times. Gives me x squared plus x. And I get remainder 1. So is 1. That means that the GCD equals 1. We passed B. Yay. And now I have to do this big thing in A. I'm supposed to compute Well, I have to figure out whether x to the 2 to the 3, so x to the 8 minus x, is divisible by f. So f of x divides x to the 2 to the 3 plus x means that if I take x to the 2 to the 3, then that's congruent to x mod f of x. Just rearrange things. But this tells me how I can compute this x cubed, x to the 8. So I will repeatedly reduce mod f of f of x. So I'll reduce mod f of x as I go. So I want to end up with x to the 8. Alright, so x to the 8 is the same as x squared to the 4 is the same as x squared times x cubed squared. How about I go with that one? So let me find some ways of splitting this. So that's x squared times x cubed squared. And x cubed, I know how to replace. I know x cubed is the same as x plus 1. Okay, so I'm putting the x squared coming from here. Instead of x cubed, I'm putting x plus 1. And I have a square here. And I should put equivalence here because I used f of x. Now I'm over f2, so squares are not too bad. So I have in here, so it's the same as x times x squared times x squared plus 1. Okay, now I have an x to the 4 there, plus x. So this is x times x cubed plus x. And I again replace the x cubed by the f of x. So that's x times x plus 1 plus x. And now I wonder what I'm doing wrong. So I'm missing some parts. Somebody help me for missing x squared. Oh, there is an x squared. Yes, x squared times 1 happens to be not x but x squared. All is fine again. Okay, now what I have there is x times x is x squared, cancel with the x squared, and I'm left with x. So this thing is congruent to x mod f of x. So I have from this thing where I'm supposed to show that x to the 8 is the same as x mod f of x, I've shown x to the 8 is x mod f of x. I'm doing this gymnastic here in order to show you that computing modular polynomials, even if you don't have a computer, isn't so hard, but also to see that, okay, degree 8 is still fine, particularly if it's with a kind of sparse polynomial where you don't get the x squared term, but you should really like your computer for the larger degrees. Now, why is this test nice for us? Well, we're looking for something where, when we're computing mod p of x, we have x to the d as 1, also known as x to the d plus 1 is x. So Rabin's test here, part A, tells us something for irreducible polynomials. So if p of x is irreducible, then then Rabin's test shows that the order of the polynomial of p of x is, well, okay, I didn't show you one more thing, but I'll add in a moment, that the order of it is less than q to the n minus 1, because x to the q to the n is common to x, so we take it away, minus 1 divided by x, so we get 1, mod p of x and one thing that I didn't show you yet, another theorem so if you take irreducible polys let's call this a set theorem. So theorem, if f of x in fq of x of degree n is irreducible, then we get that if f of x divides x to the q to the m minus x is equivalent to m is a multiple of n, so n divides m. That's also not what I wanted, wait a second. I mean, this is true, but it's not what I wanted here. What I wanted to get at for all 10 minutes, we will use the other direction, that the order yes, sorry. We don't actually need this thing. Wipe that. I'm sorry. We won't need this thing. If you ever find irreducible polys, this is true, but we don't need it. I just got myself confused. Yes?
Can't the order of px be equal to q power n minus 1?
Yes? I mean, we have examples of that.
Yeah, but it says it's less. That's what
Less or equal. But this is much weaker than what I actually want to say. What I wanted to say is, we know that if we get the q to the n minus first power, we're getting x, we're getting 1. Now, we know, we proved this for periods, that if you have a period and another way of getting 1, namely the order, then one must divide the other. You also have seen this as a general statement about groups, that if you have that some element to a power d gives you the neutral element, then the order of the element is a divisor of that. So much more important than less than is that it's a divisor. So we know that fq to the n minus 1, we're getting 1. So if we ever otherwise want to get 1, it must be an exact divisor of this thing. Now this gives us a nice speed up. Moving this up so you can still see it. If you look at some of our examples here, so we get this polynomial, then by the magic of your algebra system or by learning how to factor, you see this thing is irreducible. Then you compute q to the n minus 1, which in this case is 2 squared minus 1 is 3, and you know the order must be divisor of it. Now nice enough 3 is a prime, so you know it will be 3. In this case, it's 3, so 2 cubed minus 1 is 7. Again, it's a prime. So without doing any effort, we can actually read off that the maximum period must be 4. Then we get a nasty case where we have no clue how to do it because this is not irreducible. Then we have a case where we're still in the speculation state, but let's assume we had found just that polynomial, the x cubed plus x plus 1, where we just proved it's irreducible. Then we know this guy has order dividing 7, so must have order 7. And here we get our first mystery, or our first, we don't know the solution yet. Because 16 minus 1 is 15, and 15 is not irreducible, is not prime. So for that polynomial, we actually have to test this. We have to test whether the order is 15, or maybe it's just 3, or maybe it's just 5. But for everything where the q to the n minus 1 is a prime number, we don't need to do any of the nasty calculations anymore. We just know, well, x mod p of x is not 1, so the order is not 1. So the only other possibility is 3 or 7 or 7. For the 15, we would have to try whether it's order 3, whether it's order 5. And if it's not 3 and 5 and 1, then we know it's 15. So this saves a lot of effort. Order, well, of C or P, because we only need to test divisors of q to the n minus 1. So here, in our case, we had x squared plus x plus 1. First observation, we need to check whether it's irreducible, which it is. So this thing is irreducible, so we can use this. Then we take 2 to 2 minus 1 is 3. So the order is 1 or 3. And obviously, x is congruent to x, not congruent to 1 mod x squared plus x plus 1. So we get order 3. Similarly, same for the x squared, x cubed plus x squared plus 1, and x cubed plus x plus 1. Then for the factor over here, the x to the 4 plus x cubed plus 1, we get that 2 to the 4 minus 1 is 15. So we need to test x cubed. While we're using modular polynomial of degree 4, so at x cubed nothing happens. So x cubed is still 1, not equal to 1 mod x to the 4 plus x cubed plus 1. And then we test x to the 5, the other divisor of 15. Now at that point we need to do one reduction. We need to reduce x to the 5 mod x to the 4, so we're replacing an x to the 4 out of there, so we're getting is congruent to x times x cubed plus 1, which is still an x4 in there, so that's x4 plus x. Again, we're replacing the x4 by x cubed plus 1. And then we have plus x. Important part, this is not congruent to 1 mod p of x. And from that, we conclude that the order is 50. Now, of course, you might feel better just trying whether 50 is working, or at least you have an idea what it could be. Now, we still on Monday need to figure out how to do all these combinations and what that actually means for the LFSR, where these things come from. Dealing with powers is a lot more nasty. So these things are harder to predict. But nice products or irreducible polynomials, now that we understand how to deal with them, all we need to do in the future is say, okay, we compute the characteristic polynomial, we factor the characteristic polynomial. I do expect you to be able to do small factorizations such as tests of whether 1 is a root, recognizing that this polynomial is irreducible. So let me put this at the end of this remember list, and I'll make a longer line here. Remember x squared plus x plus 1, x cubed plus x plus 1, and x cubed plus x squared plus 1. These guys are irreducible. You should be able to do division with remainders modulo some polys, but all of those will be over F2. And then you should also remember that you only need to test if it's so for irreducible polynomials. Only need to test q to the n minus 1 divisors of a. Only test divisors of q to the n minus 1. All right, it fit on the board, it fit in the time. This is the list of things you should remember. Of course, we have developed those. You should understand how we got there, but for your daily tools, these are the things you should know. So it's not as scary. And oh yeah, there was one question about homework. I will post a homework sheet today. You have 2 weeks for that. That's mostly because students in last year were like, oof, there's nothing, then something. So at the same time, unfortunately, they copied my announcements, or the statement, the moment when I could have changed my announcement was a long time ago when I didn't notice. So I promised only 2 homework sheets. So that means there's a homework sheet, it's out now. You can't solve the second part. You can solve the first part. So you basically have 2 weeks for the homework sheet, where it means the first part you can solve now, the second part you can solve next week. So if you want a more even workload, start now. If you want nothing, another week of freedom, you get a bigger spike then. Okay, see you Monday.